Hello, and welcome to the OpelX podcast, bringing you candid and open discussions about all things in the power electronics world.
This show is a part of the Open Power Electronics Network. Visit us online at opelex.net. That's opelex.net for show notes, articles, tutorials, and a whole lot more.
My name is Abhijit Kshirsagar. Currently, I am a professor at the Indian Institute of Technology, Dharwad, where I teach and conduct research in the Electrical Engineering Department.
And I am Lalit Patnaik. Currently, I am a fellow at CERN, Geneva, where I work in the Beams department designing power supplies.
Lalit and I were colleagues at the Indian Institute of Science, Bangalore, where we both completed our MTech and PhD degrees in the Power Electronics Group at the Department of Electronic Systems Engineering, DESE.
Over the coming weeks, we will be talking to leading academics, industry professionals, entrepreneurs, and other leaders in power electronics and allied fields. We hope you will find this useful and entertaining. So sit back and enjoy.
So our guest today is Professor L. Umanand, who is a professor at the Center for Electronics Design Technology, which is now known as the Department of Electronic Systems Engineering, DESE, at the Indian Institute of Science, Bangalore. Professor Umanand, can you hear us?
Yes, I can hear you.
Great. Could you tell us a little bit about yourself and what you do at IISc?
I am an electronics circuit designer. I did my schooling all in Bangalore, education also all in Bangalore. My bachelor's background is in electronics and communication. So actually I'm a communication engineer. Of course it was way back when it was discrete devices where you use transistors, BJTs discretely to build transmitters and receivers. The ham circuit radio time period. Okay. Of course now later the circuits graduated, they became integrated circuits, and now even the super heterodyne receivers you have an IC which we used to build discretely before. Then in the masters was focusing on electronics design and technology. That is where I made a shift in the level of power of electronics. So it is still analog electronics, but gradually lifted myself up to a slightly higher, more higher power, and then we call it power electronics, and that is how I began. We had a very good teacher. There was a teacher called Professor Ramesh Bhatt, and he was teaching us power electronics, solar, renewable energy, bond graphs, all those things. And it was very inspiring. In fact, at the time of BE, when we came out of BE, when we passed BE, power electronics was very fearsome. We were all terrified about power electronics, especially drawing the SCR waveforms, the waveforms across the anode and the cathode. But after we came to masters, the whole thing changed. In fact, the transition from bachelor's to master, it was totally negative. You had the full confidence saying that I will never again enter power electronics. That kind of confidence. And then with that kind of a very strong negative conviction, we entered masters. And that is where Ramesh Bhatt really made the difference. He converted the negative to zero and then to positive, and then now I am a power electronics engineer. So we had to make the long story short. And working in terms of DC-DC converters, power conversion, inverters, DC to AC, renewable energy, photovoltaics, all these motor drives, electric vehicle, these are all the passions which we are working on.
Very nice.
Good to know. So, could you tell us a little bit about your day-to-day activities? I'm I'm sure you're teaching, you're conducting research, you're conducting a lot of outreach activities. Could you just in brief describe what your average day looks like?
Yes, teaching actually is less. You see that we in a semester we take a three credit course. A 3 credit course implies that you have 2 hours of theory in a week, 2 hours of theory in a week, and one session of lab of 3 hours in a week. So that is how it is timetabled typically for a course. But most of the time it doesn't fit in those time frames, especially the lab sessions. So the lab sessions go on all the week. Because one is not able to complete the laboratory work in one 3-hour session, the students take multiple sessions. So most of the time it is a 4-day lab session for the students. You still have 2 hours of theory in a week. So typically on a day when I am having a theory class, 1 hour mostly in the morning session, I prefer either in 9 to 10 as my lecture hour, or if sometimes you see what happens is that it is very difficult to set the timetable. So this semester, like I am taking it between 12 and 1. So still okay, as long as it is before the food, because otherwise people will start sleeping if it is after lunch. So just before lunch, in fact, it is very interesting in the sense that I find students very awake. I think because pangs of hunger make them not to go into sleep mode. So therefore 12 to 1 is also nice. Abhijit.
Yeah, so can you tell us a little bit more about how you manage to balance out research, what you're working on, and any other activities other than teaching and research?
Actually, it is very difficult to draw a line of demarcation between implementation and research. They are all highly coupled, intermingled. But we have students, different types of students. You have the master students. Master students do kind of a closed form kind of work because they are curriculum driven. They are having just 2 years, and in the 2 years everything is straitjacketed and everything is given within starting ending time spans, and they have to deliver it in that time. So most of the work that the master students do are closed form. You know that it will work within this given time. And then the other type of students are the research students, the PhD students, and these students take up open-ended problem where we don't know when the end time is. In most cases, means whether a particular concept will work or not. So what I have been following right from beginning is that the research students work on nice innovative concepts which are probably not touched upon in the world, and once the concepts start formalizing, means you know that okay, the concept is right, we can go in this direction, these are implementable things, then that a portion of that is offloaded to the master student to do the closed form solution implementation within a specified period of time. So in this way, not only is there good interaction between the masters and the PhD students, they mingle a bit. Otherwise, they don't see each other, and then that what you call the contact with seniors and juniors gets lost. So this way we try to keep some kind of an overlap in the problems, though they are all working on different knowledge levels. Lalit.
Could you tell about some of the more interesting projects that were memorable in some way for you over all these years with different students? It could be research students or even master's students.
Yeah, a couple of them are there. One of the nice challenging projects was not actually in electronics. It was in desalination. There was this project by the student Ravinder Kumar. And it was an interesting part where you try to increase the flow rate of the distilled water. Okay, the idea was that you take the seawater and distill it, flash distill it, and you will have the distilled water having the salt content, mineral salt content much better than tap water, normal tap water that you get, the Kaveri water, the river water. So so in one stage distillation itself, it comes close to the tap water. Two stage distillation becomes much better than. So in fact, you can also add afterwards to the distilled water salts that you prefer, nutrient salts, and people can use it as drinking water. So that is the idea. If you use membrane, the seawater with membranes is very tough on the membranes. You will have to keep replacing the membranes by reverse osmosis process. It doesn't work out, becomes very costly. So therefore we try to use this method, and then there was a concept called pressure modulation, where the vacuum pressure, the pressure in the chamber was less than atmospheric pressure. So that was modulated to adjust the boiling point of the liquid, which is the water. Mm-hmm. So normally the boiling point is supposed to be 100 at mean sea level, and at Bangalore it was around 93 degrees centigrade. It also varies with the pressure. So we wanted to bring down the pressure, boiling point, bring down the pressure further so that the boiling point is happening at a much lower temperature, because the temperature of the solar water collector was at around 70 degrees. So we thought we will try to bring in lower. But there is a kind of a break even. You can't keep bringing it lower and lower by increasing the pressure, because you are putting more energy into the pump, the pressure pump, the vacuum pump. So there is a break even. So the remaining enthalpy we try to make up with the heaters. So this way we were able to achieve some degree of improvement in the flow rate of the distilled water. So this did not have any electronics. It was only a thermal. So that was the first time we got to model a thermal system using bond graphs. And thermal domain is a very interesting system, because it is a domain which does not have dissipation in it. And thinking of the entire energy system where there is no dissipation, there is no loss, because every loss is a source. It was an interesting, it was a very, very interesting and also challenging thing to model from scratch.
Actually, one thing that comes to mind when you talk of a project like that, in fact, the first one that came to your mind is that coming up as a circuit designer or electronics designer, how is it that something that is completely away from electronics, in some sense, completely different engineering domain, how is it that you get into those kinds of problems while still having a background in electronics? What gave you the push?
Yes, that is correct. Actually, in fact, people should not make these kind of distinctions. Initially, yes, we had a lot of these kind of distinctions. When you finish your BE, we are still not mature. And okay, I want to do VLSI, I want to do mechanical, I want to do. Actually, if you see in the entire knowledge domain, there are two parts. One part is physics, which is dealing with the inanimate, and there is the other part, which is the life sciences, which is dealing with the animate. These are actually the two knowledge domains that are existing. And from physics, actually anything, you see, if you actually you take a physics book, you take Dr. Feynman's series of physics. You take any physics. In any physics, every chapter, there will be a chapter on electrostatics, there will be a chapter on magnetics, there will be a chapter on fluid dynamics. So all the branches of engineering that we understand and come to know today are actually part and parcel of the physics. So if you look at that in that fashion, physics as the mother of all the inanimates, and try to visualize in that fashion, and if you work in the energy at the energy level, in fact that is one of the insights that bond graph gives, you are domain free, and you lose the fear of domains, and that is precisely what an engineer should do. Should not be afraid of a domain, and you should not have a limitation. My domain ends at this point and someone else's domain begins at that point. It is one single continuum.
Since you mentioned bond graphs, and many of our listeners might not have heard of bond graphs, it's not a popular kind of area. So maybe you could tell a couple of words about what is this bond graph and why is it that you want to use it in engineering?
Correct. Even when we studied in BE, during our times also, bond graph was not there in the undergraduate education. Though I feel that it is a must, it should be there. We were also studying through block diagrams, where you are only talking in terms of signal flow. You are not at all having an insight on what is the next block to which you are connecting, what is the input impedance of it, what is the feedback effect. All those things don't come out nicely in the block diagram. But once we entered masters, and our teacher I mentioned earlier about Ramesh Bhatt, who introduced us to power electronics in a very, very different way. He in fact introduced bond graphs to us, and we saw the connectivity among all the domains. So you see that in bond graphs the modeling is based on energy. So energy removing all the domain aspects has only two possible parameters, which is effort and flow, and they become the states, the effort variables and the flow variables, and energy storage by virtue of flow, energy storage by virtue of effort. So based on this, you see that it moves across domains in a very seamless manner, and you could kind of model, not only understand, but model and also try to synthesize similar equipments in another domain. Like for example, one of the students, Prasanna, who was working on controlling the flow of heat captured from a thermal collector and putting it down into the kitchen, so that the person who is cooking need not have to come to the rooftop and do the cooking on the rooftop, so that the person can still stay in his own kitchen, and you direct the energy to the kitchen. So there he was controlling the flow, so he had to make a very, very low flow rate meter. So for that, such a low flow rate meter was not available. It's still not available. You have to make it on your own only. And he used the principle of doing it. He did all the complete. See, it is basically controlling current. Controlling current, he knows how to do in the electrical domain. So he did all the complete detailed circuit and analysis of controlling current. And he put it through the bond graph, and then he took it out into the mechanical domain, and whatever came in the mechanical domain, he implemented the components as is, and he got his flow meter without having to know fluid dynamics and all those things. So that was an interesting another sub project in the PhD work. He also patented it, nice, and it was a nice work. It worked successfully, and he was able to use. He had to make two of them to control the downflow and the upflow, and implemented that.
So to talk about your current research focus and your big picture sort of vision for your group and your research focus, what do you think are the next big challenges or the big ideas that we need to focus on for the next 20 to 50 years? Of course, both of us, Lalit and I, of course, know a lot about you, that we know you are not restricted to the power domain or even the electrical domain, as you have just described with your earlier projects. But again, domain agnostic, what do you think are the big problems that we need to tackle in 20 to 50 years from now?
See, one of the nice challenges that you will see, the upcoming challenge, the next 20 years, 20, 30 years, the prime moving will be an interesting part coming into the picture, coming into everyone's life. E-mobility, what we call. So as you see, like the cars, it may not be in the form of cars, or it may be in the form of individual locomotion, or it may be in the form of two-wheelers, three-wheelers, four-wheelers, locomotives. The prime mover, that prime motion, what you get now, that would become the mover of the movers of the world. So that prime mover design is an important thing. So right now, if you see, a lot of people are experimenting on that, researching on that. The permanent magnet based machines, PM, SM, synchronous machines are becoming popular, but they are not the solution. In fact, people are moving away from that because of again monopoly in the sense that there is only one country which has total control on the permanent magnet, the rare earth material. So people don't want to have someone beating down your back, saying that okay, you have to do this and not that, and things like that. So people are researching on non-permanent magnet machines, where the synchronous reluctance machine is one such thing. And our students are working on what is called as the electromagnetic synchronous machine, where the idea is that you still have your cylindrical rotor just like your induction machine, but instead of permanent magnets in the rotor, you have electromagnets. But if you have electromagnets, you have to supply power to the rotor without slip rings, without brushes, non-contact. So you have to have a rotating transformer, very small one, because you need to only supply the magnetizing energy, and that rotating transformer will be supplying the power to the rotor electromagnets. So you have the electromagnet rotor and have an electromagnet synchronous machine. So you will need two inverters, at least two inverters, one for the main power and another for supplying the power to the transformer like part of the laminations and these kind of things. So synchronous reluctance machine is also becoming popular, and right now synchronous reluctance machines are salient pole types, which are much more difficult to make. Again, people are researching on, can you have virtual saliency? Can you have a cylindrical rotor with virtual salient poles? These kind of things are being worked on. So that is one aspect. That is at the level of a component, a machine, the prime mover machine, which can scale from the very small prime mover, which probably may be needed to move the wrist, yaw, and as they would use in the robots, to locomotives which are real powerful, gearless, brushless, slip ringless, those type of machines. So this will be a huge domain which people need to work on, and a lot of scope for that one.
So if I hear you correctly, you're saying that it's more machine design as well as how to drive these machines. So there's a synergy in the magnetics, machine design.
Yes. System wise, more and more people will go for automation, because I think the life will change now. It will no this distance, social distancing, as you see, will continue, and it will become a norm. And automation, and probably you will interact more with robots better and things like that, and you will interact only through the video conferencing. Right. More and more this will start happening as the new normal. Yes.
Since you mentioned about the prime mover research on motors and
yes.
Different kinds of motors and stuff, what are your thoughts on the research on energy storage aspects? Because that is again one thing that is very important going into the future with renewables.
Yes.
And electric vehicles.
Yes. Storage is going to be a tough problem. There are two things. Lithium ion, of course, is the one which looks to be most popular, but that is not one which probably may be the one which will be the backbone. There are a lot of other things which people are investigating on, like the nickel ion and things like that one, where the focus is on life. I need 20 years life for the battery. One is high power density, high energy density, which is needed if you want to keep it mobile and take it onto your vehicle and move around, things like that one. Nickel ion is actually having low power density, but one fantastic feature of nickel ion is that it is having a huge life, long life. 15 to 20 years is the life expectancy that but it is huge, so which means that you cannot use it in mobile applications. But it is having a really good application which could make the backbone for the country, in the sense that, as you see that due to the coronavirus, one very positive benefit is that the nature is coming back into its own. And we are also signatory to the Paris Convention, which means that you are not supposed to use fossil fuels for generating your energy supplies, anything from the ground. So therefore, you need to use renewable energies, and the renewable energies are distributed. So you get it in daytime, you get the sun power in the daytime, and for the night time, what you do, you will have to store it into some kind of a storage system. So most of the thermal plant people, like the Lignite Corporation of Neyveli or the NTPC the thermal companies, they are all now trying to shift their mode of operation, their focus of operation into renewable, because they have to gradually phase out, make it to zero, the coal generation. So what will they do? So they are going to get into storage, and they are going to store with the batteries on the real estate, so they are not bothered about the weight. So nickel ion there can play a huge role. They will have fields and fields of storage where the life will be very huge. So in the daytime you keep pumping into this storage. In the night time it will buffer out. Basically buffering will be through this. So these kind of things will happen with storage. Renewable, because if you want to use renewable energy, whether it be wind or photovoltaics, you need to have huge amount of storage. So some storage which has a fantastically long lifespan is probably going to form the backbone, especially when you want to do it over the day, all 24 hours powering the country.
So I think you made two interesting points. If I just want to capture the essence, is that for buffering renewables, we don't need very high power or energy density, but we need long life, because once that system is installed, you cannot be changing it over and over again. And the second thing is, you are saying that it has to go in the right place. So current plants already have the land, they have the infrastructure, presumably they already have the power system infrastructure in place. So adding batteries doesn't really incur much cost, whereas installing batteries of that size somewhere in a different location presumably requires power system investment also. So
precisely.
Just to sort of inspire these new students who are going to be listening to our this podcast, what do you think are the key areas that students who are currently in their BTechs or just about to go into a BTech program, what is it that they need to focus on today so that they are going to be effectively well trained and in a good position to tackle all these challenges once they become professional engineers and once they enter their careers?
Yes, especially the students who are working in the electronics background, like the electronic communication, electrical engineering, EEE, those kind of background, those kind of streams. The students should focus on implementation. Implementation is the key, and they have to understand the working of the circuits. It should get internalized. It should not be just for passing the exam. they should understand how the circuits work, and they should be able to build an interface. See, basically electronics is nothing but building interfaces. You are interfacing, you are on the left side you have something, and the right side you have something, and in between you are building some electronic gadget or electronic circuit which is going to interface the left to the right. And it could be power, it could be low power, it could be high frequency, it could be analog, it could be signal level, whatever it is nothing but an interface. It could be a signal interface, it could be a power interface, it could be an analog interface, it could be a digital interface. So given any set of, so when people are studying block diagrams, which says the output of the block diagram, which is a single arrow, is actually having output impedance 0 and the input impedance as infinite. So they should actually zoom that, make that more non-ideal, and given two blocks, and how do you interconnect block 1 to block 2, the output of one block to the input of the other block, by making an interface circuit. And that interface circuit should be compatible with the V's and I's of the input and V's and I's of the output. Then they will have a much more seamless kind of a background, where they can actually shift from microelectronics to analog electronics to power electronics to digital electronics, control electronics, all those things, without having to say that, okay, I am specialized only in instrumentation, I will not work on power, and I am specialized only in machines, I don't know about magnetics. So like that, they should not this one.
Okay, maybe I will ask one more question. This is again regarding the research methods, or the way you try to inculcate a culture of innovation and coming up with new research problems. Do you have some methods which are general, in the sense of irrespective of what a particular student is working on, you try to use these practices in the lab to inculcate a culture of innovation or coming up with new ideas?
Yeah, the research is actually a tricky topic. See, up to a master's, you can have a kind of straight-jacketed way of doing things. So once you finish master's, you are in the world of synthesis, where you have no references. You are the pioneer, you are breaking the path, you are making a trail for yourself. So each student must feel that whatever he does, it is his baby. The guide will of course be there to handhold and to give gentle directions and probably even help and support. But it is the mental maturity of the student. See, the whole point in research, why do you say PhD, doctorate in philosophy? You're not getting doctorate in electronic design, right? You're not getting doctorate in biology. You are getting a doctorate in philosophy. It's basically a kind of meditation. So when you meditate, you are kind of contemplating, and the process of contemplating achieves one particular change. And it is actually very, very abstract. The change is in your mind. So your mind has matured in that 5 years period. And that is actually the output of the PhD process. A spin-off and fall-off is a thesis that you will get. So you have to view it in that kind of a context. So this thesis or this thesis work is your vehicle for meditation to uplift your mental maturity to a level of philosopher. So that is the thing. So one important criteria that you should tell your students are the students who are going to do PhD. It is not a degree that you get on a piece of paper. It is something more, much more. It is a well-being. It's a wellness program actually for your mind. And you have to enjoy it. You should be passionate about it, and you should want to do it. Then only you will contemplate. If you don't contemplate, it won't work. So that process of contemplation is the one which is the key. And to bring that process of contemplation, you should like to do that. And to do that, you have to choose the topic what will give you the passion, and you'll say, okay, this is my baby, this is going to be my baby, I want to go in this line. Then of course the guide plays the role of pushing you, and then probably guiding you and hand holding in some points and times of difficulties, things like that one. So then once you have come out of that, then you are a much more stronger individual where you can do wonders. So that is basically the point.
Actually, this also very nicely summarizes why we talk of PhD holder as an independent researcher. They are supposed to finally become an independent thinker in a way.
Exactly. He should become an independent thinker, innovator, wise.
I think it's interesting that in this entire discussion you never mentioned paper or publication.
Yes. They're all spin-offs.
Okay. So
would you want to say something on publications actually? Since we mentioned research.
Yeah, publications, everything is, whenever something is taken in moderation, everything is all right, everything is fine. You would have actually done a lot of things where other people will not know, and knowledge is something that you need to share, and sharing can be in many platforms in many ways. As the old saying goes, knowledge is the only thing which increases within you when stolen, and that is the important point that one should take away. So one should not keep it hiding. And being in academics, you will want others to steal as much knowledge as possible, so that it increases within you more. So thinking in that fashion, one should, whatever knowledge is there, try to put it in some platform. It could be publishing in a journal, or it could be publishing in open source areas, ebooks, and even books, so that it can disseminate to more number of people. And the more free it is, the better. But then what has happened is that in many places, the publications have become a kind of a bean count or a number counting mechanism for one's career development. So which has kind of come and distorted the whole concept of publication for knowledge sharing. But publication for knowledge sharing is still a very worthy thing to do.
Mm-hmm. There is also the side aspect of peer review, because of which in the research domain there is a great emphasis on publishing in journals, let's say, as opposed to a blog or an article on an open website. So what is your take on that aspect of publishing?
Yeah, people go in for this type of peer review kind of a thing to get a kind of a weightage. So the weightage is for what purpose? The weightage is for the purpose of self-career development. So if you remove that purpose of self-career development, okay, I will not tell the young people to do that, but if you remove that, if you look at it as just knowledge dissemination, then whether it is peer reviewed or not peer reviewed, it really doesn't matter, because most of the concepts and most of the things that people learn on the internet are not peer reviewed, but there are a whole lot of fantastic diamonds which are there, precious tidbits which are there in the internet, which are not peer reviewed, and which has helped many people, and it has kind of triggered other knowledge reactions on other people. So it is not necessary that it should be peer reviewed, but when you are in a club, and in the club, if another person has to respect one another person, then this peer review concept becomes a very important thing.
Very interesting.
So just to summarize, I think we hit on all the questions that we wanted to. Were there any other points, sir, that you wanted to talk about but haven't covered?
It is fine. Yeah.
Okay. Yeah. Thank you so much for your time.
Okay. Thank you so much, sir.